So in this segment, we're going to continue our discussion and of the relationship between free energies and equilibrium constants. So let's switch over to the lecture objectives here. We're going to be looking at how to calculate standard free energies from equilibrium constants and vice versa, and using the Van 't Hoff equation to relate equilibrium constants and reaction enthalpies. We can actually figure out not just reaction free energies, but reaction enthalpies as well. Okay, so at equilibrium, right, and we sort of previewed this before, at equilibrium, the free energy of the reaction in its current state is equal to the standard state free energy plus RT ln Q. But of course, at equilibrium, the reaction is neither spontaneous nor non-spontaneous, so the delta G is 0, and that is going to be equal to the delta G standard state plus RT ln, now the Q at equilibrium, which is of course just K. So the free delta G standard state is equal to minus RT ln K. So you can find the free energy, which combines the enthalpy entropy together by just taking minus RT times the logarithm of the equilibrium constant. So you can see that the equilibrium constant and the free energy are really just the same way of talking about the same sort of things, which is really powerful, right? The free energy, which is a combination of entropy and enthalpy, can be related to the equilibrium constants that we've seen before, which have nothing to do with thermodynamics, right? We don't do anything about like measuring heats or anything when we look at the equilibrium constant. So this powerful connection between experimental observables of concentrations and partial pressures and energies and entropies from measured as heat transfer. So it's really quite amazing that we can connect those two seemingly disparate things, the amount of energy moving back and forth and the amount of entropy, connecting that to actual measured concentrations when the reaction's at equilibrium. So, since there are essentially different ways of talking about the same things, we can actually sort of tabulate what all the possibilities are. So if the standard state for energy is less than 0, then log K has to be greater than 0, which means that log K is greater than 1. And so the equilibrium mixture is mainly products, right? Because delta G standard state is less than 0. If delta G is greater than 0, then log K has to be less than 0 because it's just, linearly related times minus 1. And K is less than 1, which means the equilibrium mixture is mainly reactants. Now, if the standard state delta G is equal to 0, log K is equal to 0, K is about equal to 1. So the equilibrium mixture contains comparable amounts of reactants and products, K equals 1 for 1 molar concentrations, 1 atmosphere partial pressures. So that's how we can relate those two quantities, delta G standard state and log K. And you might think, well, what if I'm measuring things in pressures versus concentrations? That's okay. Because remember, the standard state for gases is defined as 1 atmosphere for both K and G. If it's for things in solution, then the standard state is defined as 1 molar for both K and for G. So it's really, you don't have to worry about units as long as you're using the same standard state, the same definitions of the standard state for both your free energies and your equilibrium constants. And if you are, then this relationship will always hold. But you can't like do your K, you can't tabulate delta G's that involve using partial pressures and then calculate Kc instead of Kp. You have to use the same standard state for both of the quantities. Calculate Kp for this reaction. Okay, we're given a reaction and we're given a standard state free energy. Can we figure out what the Kp is such that we can then go in, plug in concentrations and solve for what equilibrium concentrations would be, right? So given the free energy, that's really the same thing as being given the Kp since they're all gases. 1 atmosphere standard state. And so delta G star is equal to minus 33 kilojoules per mole is equal to minus RT ln Kp. And so we need to just plug in R and T. We know that a delta G star minus over RT is just going to be equal to log Kp. And so this would be minus 33 kilojoules per mole divided by 0.008134 kilojoules per mole Kelvin and 298 Kelvin. And so now we've got kilojoules per mole on the top and the bottom. And this is going to be 1 kp. And so once we plug everything, remember this is minus kilojoules per mole, it's minus delta G, so that's a plus there. We get 13.31. Sorry, reverse that, 13.31, just when we plug everything into the calculator. And that's unitless because the kilojoules per mole are canceled out on each side, equals log Kp. And so Kp is therefore e to the 13.31, which is 6.0 times 10 to the fifth, right? And so that will be equal to NH3 squared over N2 H2 to the third at equilibrium. So really, if we're given a standard state free energies or KPs, KCs, depending on what the standard state is for whatever species you're looking at, those give you the same information. So thermodynamics gets connected to, or thermochemistry gets connected to equilibrium concentrations.